Short introduction to the Saint-Gobain multi-comfort program. Based on the habitat customers' needs and the different zones and cultures here, this program it's aiming of satisfying the needs of the different clients, taking into account the products, the systems, and trying to look at it in a more holistic, from a more holistic point of view. The key points here are the fact that it combines together energy efficiency, inhabitants' comfort, and all the solutions, and the final solution, to be more correct, should be accessible in terms of cost. Now, the main dimensions of comfort to which we are looking at are those which you can see already here. We are speaking about the design, we are speaking about the thermal comfort, we speak about acoustics, we are speaking about light, we look at air quality, which should be something that it's easy to run and maintain, and last but not least, it should be sustainable. The main reason for which we are looking at all of this, and we will see them a little bit later in more details, is the fact that each and every one of these are affecting the way that the human perform in the building. So in the case, if you look at the thermal comfort, in the case of the overheating, you will have a decrease of the performance. If you look at the noise, you can see that about 65% of the persons which are working in the offices, and mainly in the open offices, they are distracted by the too much noise. You can have lower performance up to a factor of 10% if the quality of air is bad. And by allowing the people to have natural light, daylight, you can increase the productivity by as much as 20%. So all of these, they are adding together, and this is one of the main reason for which you have to look when you design at all these dimensions. Now, the multi-comfort itself, if we are speaking about criteria, it has a set of criteria that you can see here. It speaks about energy demand, it speaks about cooling demand, it speaks about daylight, about thermal comfort, acoustics, and so on. We are going to take them one by one, and during this first set of online trainings, we will discuss, and we will have a dedicated session of trainings for each of these criteria. Furthermore, in the second part of January, probably beginning of February, we are going to have a second session of trainings where we will speak again about this dimension, and we'll look at some different points of view. Now, the main challenges, if we are speaking about the energy performance, will be linked to the space heating and cooling. And you can see here the way that the energy is used in buildings. If you look at the European data, you can see that about 40% of the total consumption, it appears in buildings. So this being said, you have here on one hand or upper image the way that this consumption, it is split between the different needs. You can see that in the moderate climate you have about 75% of the energy who is used for the heating and cooling, while in the hot countries, and this year task as is situated in Spain is basically a hot climate, you have a slightly different pie. About 46% it is used for heating, and about 16% about 20% it is used for cooling. But altogether it will come nearly to the same result. It will be about 66%, so about 2/3 of the energy which is used for either heating or cooling. Now, if we speak about the different perception of comfort, I'd like to share with you some of the findings that we had about the people's, let's say, comfort issues. This is one of the studies done, and you will find many of this in Germany. The question, which problems do you have with your room, with your apartment, with your house? The first 3 points which are always coming are the thermal insulation, the noise control, and the humidity. So these kind of issues, they appear more or less everywhere in Europe. You will find them in Russia, you will find them in Turkey, and almost everywhere in the world. Now, speaking of multi-comfort, as we already discussed, you can see here the main dimensions of comfort, and we are going to take a brief look at each of them, and afterwards, for the incoming online trainings, we are going to detail and speak a little bit more about every one of these dimensions. So first of all, we need to speak, when you speak about comfort, you need to speak about design. Of course, having a good design is the prerequisite for a well-perceived project. And I'm going to show you some examples of houses which are combining the design as free as possible with the fact that there are also designed or respect the criteria of the multi-comfort. You can see different types of design here. It can be a single family house, or it can be non-residential space. The second dimension of comfort, which we are going to detail today, it's the comfort linked with thermal. And it's not only when it's snowing, but as we are going to see this year in the warm climate, it's also about not getting too warm in the summer. And one of the main effects of the overheating or of the thermal comfort is the fact that it is directly affecting the way the human body performs. You can see here the different results of the thermal comfort. You can see not only in the summer but also in the winter. This has a direct effect over the relative performance of work. So if you are going to design something and the inhabitants there will find that it's either too cold or either too warm, this will affect their performance, and in the end it will prove that this is not very well perceived by the ones who are managing that building. Another comfort dimension is the acoustic one, and I can share with you few data. Tomorrow we are going to speak a little bit more about this comfort dimension. About 80 million people, they are today exposed in European Union to very high noise levels. Furthermore, we are also speaking about the quality of air, and you can see here a study which is, then there is a mistake here. It's not a visual comfort, it's the air quality. It's the negative effect of the CO2. So a too high level of indoor CO2 has negative effect, and for example here you can see the performance in basic activity depending on the different concentration of CO2. The higher the concentration, the red one, which is about 2,400 to 500 ppm, the lower the performance of the inhabitant is in the basic activity. So we can connect directly the quality of air within the building with the way that the human body is performing. There is also the effect of the good level of natural light, and by allowing the inhabitants to have access to a better environment in terms of quality of light, you will see that the human body, the performances of the human body are higher. So you can see different studies, there are plenty of them, showing that the better the quality of the natural light it is, the higher the performances of the people. They get better scores in standardized tests, they're having better progress in math or in readings. Also, when we are discussing about multi-comfort program as such, we are looking at sustainability. And from a sustainable point of view, there is a very strong trend in Europe and also in CIS, I would say, pointing towards a more eco-friendly approach among the homeowners. You can see here different results from studies showing that almost in all countries which have been analyzed, 2/3 to almost 80-85% of the people, they are interested in getting some kind of eco-friendly solution within their houses. And this translates in terms of multi-comfort in EPDs for the products that are used. The EPD basically is an environmental product declaration, and it quantifies the effect that that particular product or that particular solution has over the environment. So it's important when you are designing to understand also what is the effect of the product that you are going to use from the moment that the raw material are extracted till the end that those products come to their final cycle of to their final stage of usage. So through the production, transportation, installation, duration of life while being installed in the building, and then once the building has been dismantled, and the possibilities of recycling that product. Last but not least, I will point out also another key issue within the approach towards a multi-comfort is the fact that the building as such should be easy to run and maintain, because if it is too complicated, if the end user or those which are supposed to be to inhabit that particular object, they have to find they are having to go through complicated procedure to maintain it or to run the building properly, then the people will not be happy. So this would be extremely fast glance of the different criteria of the multi-comfort. We are taking a look at the thermal comfort, we are looking at acoustics and indoor air quality, we are inquiring about the visual and daylight comfort, we are speaking about the installer's comfort, and of course we are speaking about the maintenance. Now, as we are speaking today about the thermal comfort, I'm just going to show one more time the main criteria. The first two of them, they are linked directly with the thermal comfort. So it means that it should have a certain heating energy demand and also a certain cooling demand. So these two, if we look at the comparison between different buildings, you can see here the standard, or I would say the average standard average building stock, which is situated around 200-250 kilowatt hour per square meter in year for heating and cooling. The aim is to go from here to this level, and to allow, by doing so, important decrease of the energy need and directly furthermore of the energy usage. The principle is quite simple. Instead of warming continuously the coffee, it is enough if you warm it and then keep it in a pot. You can see here an image, thermographic image of the two. Here it's just heating the environment, while here, once I have been heating it, if I ensure that the envelope is tight and there is sufficient thermal insulation, and I preserve the energy inside. And if we take a look at what it means in terms of prerequisite, if you want, or in terms of construction details, and I have selected the hot climate. If we are speaking about hot climate and the new construction, then you have here the requirements for insulation, you have the requirements for air tightness. Here is the ventilation system, and of course the information about the glazing that you need to install. And if we are speaking, as it is the case for us with the task of 2017 for the renovation, then you can see here also the requirements in terms of renovation, and the better this requirements get, the better the final performance of the building will be. There is a very interesting documentation that you can find on the website of the student content. It is called Keep Cool in Hot Countries, Isover Multi-Comfort House brochure, which I'm going to very briefly share with you. You can see it here. I strongly recommend to take, let's say, 1 hour to read this document. It's basically describing, it's a guide describing how you should think about designing when aiming for a multi-comfort house approach in a hot climate. It has been analyzed for Spain, and one of the climates that it's analyzed, it's Madrid, so you will have plenty of ideas, plenty of examples. It speaks about the comfort, it speaks about the climate and the design principles, and it gives also construction examples, and it takes a look at the ecological impact. So I'm just going to scroll down to some of the examples. Okay, here we are at the planning stage. As soon as it's going to upload, so you can see it's looking at Porto, at Madrid, and at Sevilla, and you can see different analyses. You can see here the plans of the house which was analyzed in this specific documentation. It is not exactly, but quite close to the situation that we are having in this year task, which is basically say a building with 3 floors compared to this one, which is having only 1. And okay, I'm not going to enter into more details, just to know that this is looking at all the possibilities that you are having, how to do it, different construction details, how to analyze and what you can obtain when you do different methods and you take different actions. So that would be from my side quite briefly. I'm going to ask Roland to step in and to present the part. I think it's this one, Roland.
Okay, I can do it.
Okay, great. I'm hearing you quite well.
Okay. So it's going to be I think it's adequate to the situation that not so many students online. It's going to be a fast run. Hang on. Okay, here we are. So
don't worry, because I've already been informed that I got some emails that some of them they are during the school hours, and they are going to check it once they finish in about 2 hours and a half. So you will be looked upon by plenty of eyes willing to find out more info.
Okay. So anyways, I'm going to go through the basics quite quickly, because I know that everybody who is interested in energy efficiency knows all these facts already. I don't have to talk about CO2 emission and the consequences of increasing, but I just show it because it's on the list here. But one of the big points is the postulation of the climate scientists that all over the world, a maximum of 3 tons of CO2 emission should be held, and we know that a lot of countries, including the country I'm living in, which is Germany, are far upon this border. So here the red line shows the 3 tons, and that's, for example, it's Germany. So we are about 3 times as high as we should be. And the question is, how can we come any lower? And we've seen a similar cake in the presentation of Gabriel. But the interesting part is the existing buildings. The existing buildings are having 40% of the energy usage, and that's quite similar in all the EU countries, and also in some of the Asian countries, as far as I know. That means there's a big challenge, a big possibility to cut down energy demand and lower the CO2 emission. If we build better houses, but also renovate to a better standard. And what we should do, we should limit our demand, as everybody knows by now, the demand of our energy, and the rest we should try to cover by using renewables. And only this little red tip on top can be done by fossil fuels, but we're not talking about that anymore because it's that low. We are talking about the energy demand reduction and renewables. And what we want to do actually is to have this kind of it's called here eco design in buildings. It's not so much eco only as more as it is let's say a logical way of energy reduction, energy demand reduction by increasing insulation or having just better insulation, having a better air tightness, having better glazing, having an MVHR system in all the houses, because it's again cutting down the demand, and of course having better lighting. And The rest is energy efficient appliances and renewable sources. So we have done this, or this is just a few of the houses we have done, and you can see that it's possible in every kind of building, every kind of usage, everything which is built and used by human beings can be done in a very efficient way. It's just the way the way of thinking which has to go ahead and to have this let's say overline energy efficiency is what I'm looking for. And it doesn't matter if it's a small house, a big house, a house for residential usage or not. And we have seen this just a few minutes ago from Gabriel, and I want to show one important part which was shown a bit different in Gabriel's presentation. If you are looking at the glazing, triple glazing, it's not standard triple glazing, but most of the time you will end up with triple glazing. It's not, as it was written in Gabriel's presentation, 1.3 to 1.6 kilowatts per square meter. And Kelvin, it's lower than 0.8 what you're looking for. So this is quite high end, but it's important. The 1.3 or the higher than, let's say the higher than 0.8 is in renovation. But even in renovation, you're looking for a very good envelope. And the most tricky part in the envelope is the glazing. So if you are thinking of the student contest 2017, which is renovation in Madrid, you should think of super duper glass. Yeah? So think about low E glass. Think about glass with a U value, UG for the glass value of lower than 0.8 in your calculation and also in your detailing. The rest is the same we had already. We need to have a super insulation around the house. It's the yellow envelope, and we have to have that's the blue and red line here. We have to have an airtightness around the house in the envelope. It's easy drawn, but it's difficult to maintain its on place. So if you are detailing your house, your design, think about the details. Think about the possibilities the workers have to really realize this airtightness envelope. And the rest, you know it already. It's heating and cooling demand of 15 kilowatts per hour, and the airtightness lower than 0.6 air exchange volume per hour, and an over temperature of lower than 10% of the year. Over temperature means higher than 25 K, which is very tricky in Madrid because of the climate. So the 10 important points are thermal insulation, easy to do because it's just insulating all around the house, but then no cold breaches, second very important part. It's not just putting insulation in place, it's for especially putting the insulation in place so you have no cold breaches left. Airtightness envelope, triple glazing, and ventilation, MVHR system. Heat recovery, internal gates. You have to calculate the internal gates. You can do that with the PHPP, and the external gates, which means how much sun, how much energy out of the sun do you get into your house. And that is correlation with external shading, because especially in the location of Madrid, you will have a lot of external gains, and you will have to have a proper shading, so you will have something against the overheating. And low heating and cooling demand, which means in this case of passive house, maximum 15 kilowatts per square meter here. And to just give you image to it, thermal insulation, here you can see my own house where I'm sitting right now. It's all insulated all around the house. It's a renovation. And also the roof, here you see the roof, very thick. Mineral wool insulation all around the house. And also the details on connection to the windows and so on. You see there's EPS connecting to the mineral wool, there's EPS here in the basement. So you really have to think about all the little details, how to make it without cold bridges, and airtightness. Airtightness is absolutely tricky. There's an airtightness test you can do once the building is renovated, once the building is done. But you have to think ahead, because the test is just giving you a result, but not showing you the difficulties you have to solve ahead. And difficulties like pipings running through your insulation, there is maintenance goods which you should use, you should make yourself familiar with, and be able to do your planning, so the guys on site are able to really make it airtight. Triple glazing is, when it comes to larger size windows, a quite heavy thing to move. That's why I show you this this picture here on the left side with a big crane. A big crane means you have to have a place to put this crane. So don't just think about, oh, I'm going to make a triple glazing. Also think about how to move this heavy good in place, and probably give us your idea how the site is going to be run, and then you are far ahead of all these people which are just drawing 3 layers of glass and not thinking about what's going on site. Airtightness ventilation system, air ventilation system, MVHR, manual ventilation system, is needed to cut down the energy exchange, to cut down the energy demand, and for the comfort. But the airtightness, the air ventilation system only works with the airtightness layer, and it only works by running all these pipes here on the picture of the right-hand side. These pipes in all your rooms, and these pipes have quite a dimension. So normal size or small sizes start by 80 millimeters, going to 100, 120, 150 millimeters. Normal size is 200, 250. So you have to find a place where to run these pipes, otherwise you can't install and think about it. The heat recovery system is quite easy. It's like a fridge, the size of a fridge, and you have to have one place, let's say each dwelling one or a few dwellings locked together, and one you design your own way, but it's quite easy because it's not that big. But the pipes to run there, they do need quite a space. Internal gains, it's mainly the electric plugged in, like fridges, coffee machines, and so on. You have to calculate them, and you've got the internal gains of the people. The people are producing 40 to 80 watts per hour. So it's interesting how many people are inside. External gains are a lot in Madrid, are a lot everywhere. In the hemisphere of our side of the globe, they come from basically from the south, and also from the east and the west, and you will get the numbers out of the local data. So think about it, and once you have them, you design your external shading according to the cut down you need. So because you can't live with all this sunshine, you have to cut it down to have no overheating. And the main figure for heating and cooling is 15 kilowatts per square meter a year. And we have different climate zones, you know that. Madrid is going to be, where is it? Somewhere there. Spain. Here. Here's Madrid. And you see it's quite a medium-sized green. So medium-sized green means it's quite warm there. But you have the local data anyways. Just to give you an idea, the houses you have to renovate in Madrid is a different, according to the climate, local climate, it's different, and it would be, for example, in St. Petersburg or in south of Africa. So what else do we have? Yeah. If we have moderate or cold climate, then we need to focus on thermal and acoustic insulation, air tightness, windows and doors, solar gains, internal gains, ventilation system with heat recovery. If we have hot climate, and this is just on the border what you expect in Madrid, then you see you still have the thermal and acoustic insulation, but by the size of the yellow line here on the left, you see that the thermal insulation is not that important anymore. You still do need it, thermal bridge free, but not the same size than in moderate and cold climate. And the air tightness, windows and doors, solar control, natural ventilation. We didn't have that before. Let's get back. There's no natural ventilation needed in cold and moderate, but in the warm and hot climate, you should have natural ventilation for night cooling, for example. And you should have ventilation system with cooling, sometimes dehumidification. Depends on how wet the air is in an average. But you need to think about shading, constant shading. You need to think about natural ventilation, and you need to think about cooling. This is what you need for this year's or next year's student contest in Madrid. So I'm gonna show you one new build which we have done in Frankfurt a few years ago. And you will find out a few of the principles. This is new build, but same size, almost same size than you expect in Madrid. It's 4 houses, or 5. It's house number A, B, C, and then this one is called D and E, not written there. And you see the houses are facing, here's the north, in the right corner here. The houses are facing different directions. So what we have done, I showed you the pictures already. What we've done, because it's all passive houses, what we've done is we have made different facades because of the thermal gains and the natural shading we could create by the different facades. You see here, this is the east side of the building, and I'll show you the west side. It's almost similar, because on the east and west side you have almost similar solar gains. And then I'll show you the north side, this one. No, the south side, sorry about that. The south side, you find the balconies. Why do you find the balconies here? Because the balconies give you a natural shading in summertime. This picture is done in August, and you see the natural shading is almost covering all the big windows of the living room, which is giving them natural shading. Means your overheating problem is cut down by a lot. It's not the same in the upper floor, because there you have no balconies anymore. So you have to run. We had to run shadings on the upper floor directly on the windows, which makes a big difference if you have a look at the costs. And another thing I want to show you, the gable wall facing the north is having no windows to the apartments, but only windows to the walkway area, because we did give the walkway the natural daylight to cut down the electric needs. But on the apartments, you don't find any windows, because it's only losses, and we didn't want to have these losses. And this gable wall is a thermal image, is completely insulated with no cold bridges. For example, the neighbor, same time, same night, same temperature, same minute, you see all his losses. He has also a little, a very little of insulation on the facade, but losses are very big. You see all the bricks, and you see, for example, the ceilings and so on. So what we did as a section, what we did, because there's also parking space underneath, we have the parking space outside the passive house volume, and you see the insulation running all around the building, and you also see the red line, which is the air tightness layer, running all around the building, including the MVHR system room and including the stairways. Stairways is inside the passive house volume, but all the rest, like storage rooms, parking lots, balconies, are outside. The windows are according to the daylight. Optimization are quite big, but according to the external gains, they are covered with the shading of the balcony. The balcony is about 2 meters wide, so we have no need to run extra shading on the windows himself. And the others, facing east and west, they have, we can run, you can't see it right now, but we can run external shading, which is a roll up on the window. But all these windows, as you can see here, it's the same from the inside. All these windows are running almost from the floor to the ceiling, so we have a maximization of daylight and have the daylight autonomy. For example, the legal law in Germany is 10% of the ground floor has to be a window opening, and then the daylight autonomy is reached if you have about double of this size. So big windows are needed on the one hand side to have a multi-comfort aspect of daylight autonomy. On the other hand side, you have to think about the external gain and have external shading, for example. So here's a look at the MVHR system, which serves per house, per staircase, 2 dwellings each etage, which is 10 dwellings in total. And inside the dwelling, you see these special marked areas. In the walkway, we have a raised ceiling to run the piping, and all the rest is only done by meander effect. So we minimized the size and the length of the piping. So this is again an image from the inside, from the inner courtyard to the south side facing area of the building. And you can see the differences of the facades. You see one which is more facing east, then this one's more facing west, and here south. So you can do that's the idea I'm giving you. You can do by design a lot to the requirements. That was it. So fast. Thank you.
Thank you, Roland. So, the connection was okay? Okay during the presentation? Okay, great. Thank you. So what we are going to do, first of all, if you have any questions, please share it with us. If there are no questions, I believe Henrik will have a question. We are going to prepare this for the upload, and probably within a few days this is going to be also uploaded online on the website, so that the students can have access to it and take a look at it. Sibusi, so everything was okay? Okay. There is no problem, Harry. We are going to upload this on the website, and this is going to be seen. Well, Sibusi, so it's easier this year for South Africa as Spain is closer. So yeah. Yeah, I will do that, Professor Henry. Great. Listen, thanks a lot. Thank you, Roland. We keep contact, and we prepare the one for probably end of January, beginning of November. Ilian, thanks a lot. Within 30 seconds, you can close the room. Sibu, thank you for being present.